In an era defined by technological convergence, a frontier is being forged at the intersection of neuroscience and engineering. Brain-computer interfaces, also known as BCIs. Now, this system promises not just to restore the lost functions, but also to redefine how we interact with machines fundamentally. And in this video, we'll be examining the science behind the BCIs, their operational mechanisms, and their latest innovations transforming theory into reality. Okay, we're first going to start off with what a brain-computer interface from the get-go is. Now, a brain-computer interface is a direct communication system between the brain's electrical activity and an external device. And unlike traditional interfaces that rely on physical movement from the user, such as keyboards or touch screens, BCIs essentially bypass the neuromuscular system entirely. And for your knowledge, a neuromuscular system is essentially a network of nerves and muscles that control movement, posture, and breathing. So in the context of this video and the context of this conversation, it means that there are no neural signals sent from the brain to the muscles to call for muscular action such as movement. And now this mechanism translates the neural activity into digital signals that can later be used to control software applications such as robotic limbs or even just speech synthesis systems. And the core architecture of a BCI includes the following components. First, we start with signal collection, acquisition, wherein neural activity is just essentially recorded from the brain using electrodes. And methods of this can just vary from non-invasive EEG caps to even just fully implanted microelectrode arrays. And then we move into the pre-processing stage where we just apply techniques on the raw data that we just gathered in the signal collection stage. So raw data contains noise from muscle activity, eye movement, just external electrical interference. And then essentially during this process of signal processing, we apply techniques like signal processing techniques like bandpass filtering or even artifact removal in order to kind of clean up this raw data. And then we move on to this next stage of feature extraction, wherein algorithms identify meaningful features, such as just event-related potentials, also known as ERPs, or power spectral density in specific frequency bands, or spike timings. And then we move into this next stage called classification, wherein machine learning models essentially map neural features to users' intent. So examples include things like linear discriminant analysis, or even support vector machines, also known as SVMs, or long-term short memory networks, essentially. And then we output our results. So the translated signal is then used to control an external device such as a cursor or a robotic arm or a speech synthesizer. This is essentially the output that we observe from the user, and this entire system just kind of operates in a feedback loop manner, wherein real-time feedback is essential for user adaptation and system recalibration. And it's a closed loop system, which means that it helps users refine their mental strategies in order to kind of lead to the best outcome that they want to output.